cool. B2. So this right here for this problem, it just simply, wants you to look at the two atomic orbitals and figure out whether or not you would expect them to form, a bonding interaction or an anti-bonding interaction, and like what the, type of interaction it is that you're going to get. And so if we're looking at this right here, right, so what we have is, and I just simply, right, you can also think of it as if, these guys were shaded, right? Plus minus is just a very similar approach to that. But what we can see here, right, is that, the plus of this orbital and the plus of this orbital, right, they're going to be interacting together. And then minus of this orbital, right, and the minus of this orbital are going to interact together, right? So what they're going to form is a pi bond in this case. Right? And because, right, there's the nodal plane that exists parallel to the bonding axis in this case, right, that tells us that it's a pi bond. Because we don't have a perpendicular node, that tells us then, right, that it's the bonding orbital. It's not the anti-bonding orbital in this case. The next thing, right, if we look right here, right, we can see now that we have, a positive, p orbital interacting with an s orbital, right, in the positive phase right here. And so those can interact together. And so if you draw that out, right, what that looks like is, something kind of like this right here. And so when you're looking at it, right, this right here is, the area between the two atoms, right? There's no node there, right? Because they have the same exact charge. And so this is going to be then a sigma bond, right? Because there's no node that's parallel to the plane. And there isn't, any kind of node that splits those two together, right? So that's why it stays the bonding interaction. It stays a sigma. Next, right, if we look at C, right, we have two p orbitals, right? They're parallel to each other. The difference now from A is that one of them is, positive up top. The other one is, one of them is negative up top. The other one is positive up top. And then, the reverse at the bottom. And so in that case, right, what happens is that you're going to form, a molecular orbital where right, you have a node that is parallel to the bonding axis, right, which is what we have right here. But then you also have a node that's perpendicular and cuts that bond in those cases, right? And that makes it the anti-bonding orbital, right? So that makes it the pi star in this instance, right? Because you have that interaction where you have a node here and you have a node here related to the bond in those cases. For D, right, if we're looking at this right here, we should be able to tell that this is a non-bonding interaction. And the reason for that, right, is that you have two p orbitals, but they're perpendicular to each other. And so this p orbital right here, right, it's interacting with that p orbital there, where it has about half of it interacting with the positive phase, which is fine, but also half of it interacting with the negative phase, which is not fine, right? And so those two then cancel out and then essentially, give us a non-bonding interaction because, there is no, constructive or destructive interference that happens between the two of them in those cases. So that's an important thing to think about with p orbitals and like a lot of those directional, atomic orbitals, is that when they're oriented, in the incorrect way, right, they're not going to form a bonding interaction in those cases. So, and then part E, right, so if we're looking at this right here, right, we can see that this is an s orbital. This is an s orbital. One is positively phased, one is negatively phased. And so that tells us, right, that we're going to have a node in between the two of them. And so you're just simply going to end up with a sigma anti-bonding interaction here, right? Because again, there's no node that's, parallel to the bonding axis between the two of them. But there is the one, right, that is parallel, perpendicular in that case, right, and cuts it in two. The last one, right, F, is, looking at this, right, this is a p orbital, this is a p orbital. They're oriented towards each other, right? And so what we can see here, right, is that you have a negative and a negative phase. Those are both going to overlap. And so you're going to get a huge lobe between the two of them, right? You're going to get a lobe right here between these guys. Now, the important thing to look at this right here is that we don't have a node that's parallel with the, bonding axis, right? So that tells us that we're looking at a sigma orbital. And we also do not have a node that cuts in between the two of them, right? That doesn't exist. And so that just simply tells us, right, that what we're looking at here is the sigma bonding orbital. It's just, between the two 2p orbitals. These are 2p's, right, because they don't have the little hats between those, right? And that's how you identify how to do them, right? So the biggest things always when looking at and trying to figure out whether, what each atomic orbital interaction with another one to form a molecular orbital interaction, what those look like, has to do with figuring out where the nodes are, right? So if you have a node that follows along with the bonding axis, right? So if one that's perpendicular, that kind of gives you the two hamburger buns, so to say, right? That's going to be a pi interaction. Now, if it then essentially has then a thing that slices it in the middle and like flips one side over, and now it doesn't perfectly match, so to say, right? And that, so you have a node there, right? That becomes the anti-bonding interaction. It's the same thing, right? If you're thinking about sigma interactions, right? If you don't have a node along the axis, right? So if that's like a hot dog, so to say, right? You don't have a node there for that, then that's going to be your sigma interaction, right? Because it's just simply basically a straight line. Now there may be like little ends and stuff like that that kind of go along with them, but they kind of match in those cases. But one thing that can happen too, right, is that you can essentially, right, you can cut that hot dog in half and then like flip one part. So now you have like one, the open end, so to say, right? And then you have like the end that has the little twisted thingy, right? Those don't directly interact with each other. So you basically have a node right there then, right? And that becomes the anti-bonding interaction in those cases. And so that's how all of those kind of, play out. And so practice and looking at what, can interact with what is always important. There's, especially that, especially thinking about the non-bonding stuff becomes really important when you're talking about like hydrogen interacting with other atoms, because the moment hydrogen's interacting with something that isn't another hydrogen, right, you're going to then have possible interactions with p orbitals on things, right? HF is an example. I think I did one of the videos that I have posted is hydrogen, oxygen. But in those cases, right, what you have then is, it's interacting with one of the p orbitals, right, the one that's directly oriented towards itself, but then it's not interacting with the two that are perpendicular, right, because there's no way for it to properly overlap to have, a fully positive or fully negative or fully constructive, fully destructive interference interaction in those cases to form those things. So those are the important parts there for that.